Well, let's welcome Dave, our last speaker of this workshop. And his work will also not be unrelated to alpha ruthenium trichloride, at least motivated by it, perhaps. Yeah, so Dave, right, you're from KITP in Station Q, so you're local. And yeah, please welcome.
All right. Thanks, Ruben. Thanks for the introduction. And thank you to the organizers for putting this workshop together. It's been really great. Like Ruben said, today I'll be talking about experiments that are motivated by ruthenium trichloride. I would like to first acknowledge my collaborators, Roger Mong, Benjamin Hunt, David Mandrews, and Jason Alicia. And just to check, can you guys see my cursor? Excellent. Okay. Right, so the work that I'll discuss today is about electrical probes for the non-Abelian spin liquid phase in Kitaev materials. And this may be alarming to some people because these Kitaev materials tend to be good Mott insulators. And so you might ask, how could we possibly use electrical probes in order to understand their structure, their thermal Hall conductance, and non-trivial bulk quasi-particle excitations? And so hopefully by the end of the talk, I will have convinced you that this is at least possible and definitely deserves further exploration. And if you're interested in the work, you can find it published here. Oh, there we go. Okay, so before doing that, I just want to motivate the work with the sort of standard introduction of topological order and their applications to building a fault-tolerant topological quantum computer. So in a topologically ordered system, we're typically thinking about two-dimensional materials which can realize so-called anyons. These are fractionalized particles. They don't exist in our real universe, but are very special to 2D systems. So here I've represented them with these lumps of energy by red dots. If they are non-Abelian, then what we'll find as we introduce more and more anyons into the system, the number of degenerate ground states will grow exponentially. Crucially, none of these degenerate ground states can actually be distinguished by any local measurement. So as long as these anyons are well separated, these ground states will be exponentially degenerate and provide a good platform for hosting quantum information. Okay, and so that makes them very tolerant to noise, at least in principle. Then we can imagine manipulating these quantum states by, say, taking a pair of anyons, here I've written A and B, and braiding them around one another. This will perform a rigid rotation in the ground state manifold. If these anyons are non-Abelian, then in general, these unitary operations will not commute with one another and provide us a means for which we can manipulate this quantum information, and under special circumstances will become universal for building a topological quantum computer. Even though these states cannot be distinguished by any local measurement, if we were to bring two of these well-separated anyons close together, we can do a local measurement which could tell us the joint topological charge that they carry. And this gives us a way to read out the quantum information encoded in these states. All right, with that, I would like to give my cartoon picture of how we would build a topological quantum computer and the minimal requirements. Of course, this is not going to be an extensive picture. So at the very least, we need a material which hosts non-Abelian anyons. This may be some intrinsic material like the fractional quantum Hall effect, or it could be an engineered material like these indium arsenide nanowires, or it may be simulated, say in an array of superconducting qubits with active error correction. Once we have a material which realizes these fractionalized excitations, we then need a way to control and manipulate them, measure out these anyonic states, and a way of encoding quantum information into these states, and of course, also reading it out. What I'll talk about today is aspects of both of these problems while thinking about ruthenium trichloride as the example in the back of my head. Before getting to that, I would like to remind everyone about how we would do this for electronic systems, such as the fractional quantum Hall effect or these indium arsenide nanowires. Okay, so the fractional quantum Hall effect is expected to realize the Moore-Reed state at filling fraction 5/2. This would be a state which has non-Abelian excitations. There's a fractionalized excitation which carries E/4 charge and is non-Abelian. Those states could be used to encode qubits. So here's one proposal by Bonderson et al., shown at the bottom. Because these non-Abelian particles carry electric charge, we can couple to them with electric fields. Namely, we can create this anti-dot potential, which favors trapping these electronic charges. And so we can have, say, an array of these E/4 electronic charges, of which pairs of them can be used to encode qubits into. And then we can use the chiral edge states to actually probe the bulk system. So here we can insert an electron into the edge. And in this example, the electron could either take this tunneling path T1 or tunneling path T2. And then those electrons can interfere with one another. And their interference pattern will tell us something about what particle is trapped inside this antidot. Okay, the key point here is that these systems host electronic excitations and therefore are readily probed with electronic leads. Complementary systems are the P plus IP superconductor and this Kitaev Majorana chain, which has had intense experimental activity in the last decade or so. Vortices in the P plus IP superconductor realize non-Abelian defects. They bind Majorana zero modes, and domain walls in this Kitaev Majorana chain also bind Majorana zero modes. These systems are fortunate to be, at least in principle, assembled from heterostructures involving ordinary, weakly correlated materials, such as semiconductors with spin-orbit coupling, S-wave superconductors, and local magnetic fields. Now, although the Majorana zero modes are charge neutral, they still carry a fermion parity degree of freedom, which makes them amenable to electrical detection and electrical probes. Okay, and I should say if there's any questions, free to interrupt me at any time. All right, now the main player in today's talk are spin liquids. So here the microscopic degrees of freedom are spins, and the sort of typical examples I'm going to be considering are Mott insulators. So the gap to a charge excitation will be very large and inaccessible. And the kinds of systems I would like to think about need to have an emergent fermion in the spectrum. That's crucial for us. I say an emergent fermion because it arises as a collective excitation of spins, and there are no actual physical fermions in the system. So generally, these are strongly correlated materials. They'll realize a number of fractionalized excitations. In the what I'll be focusing on today are materials that realize the Ising non-Abelian topological order. And so you might think that it's more natural to control and manipulate these systems with magnetic fields. But what I'd like to focus on today is sort of complementary probes involving electrical leads. So the prototypical example for the Ising non-Abelian topological order is the Kitaev Honeycomb model. And I will review it rather briefly because we just saw this in Johannes's talk. So the Kitaev Honeycomb model lives on the hexagonal lattice with 1 qubit per site and has these strange bond-dependent interactions, which here are labeled by these red, green, and blue links. Across the green link, we have a sigma x interaction. Across the red links, we have the sigma y interactions. And across the blue links, we have sigma z interactions. And then we can also add an external magnetic field. Note that the system is highly frustrated since all of these terms anti-commute with one another, or at least overlapping terms anti-commute with one another. Now, Kitaev cooked up this model because there's actually a very elegant way to solve it. He did this by replacing each spin degree of freedom, so recall the spins live at the sites here, with 4 Majorana fermions. Now, 4 Majorana fermions span a 4-dimensional supervector space consisting of 2 even fermion parity states and 2 odd fermion parity states. And so Kitaev encoded the spin degree of freedom into the even fermion parity states of these 4 Majorana fermions. In this notation, I've labeled the 4 Majorana fermions Bx, By, Bz, and C, all associated with site J. Imposing that we live in the even fermion parity subspace means that any wave function must be invariant under application of the on-site fermion parity operator d sub j. And this is the mapping between spins and Majorana fermions. All right, now the magic of this model is that you take this mapping between spins and Majorana fermions and plug it into this Hamiltonian up here. And what one finds in the absence of a magnetic field is a system of free Majorana fermions hopping on the honeycomb lattice. In the absence of a magnetic field, this results in a gapless spin liquid, which I've shown here by this Majorana Dirac cone. When one adds this magnetic field term back in, you find that the gapless spin liquid becomes gapped and realizes the non-Abelian Ising topological order, at least when the coefficients of these 3 terms are tuned to be equal. All right, are there any questions at this point? If not, I'll continue. Okay, so then around 2009, Jekeli and Kahulin proposed this nice way that we may actually realize these strange bond-dependent interactions that Kitaev was proposing in his 2006 paper. The way they did this is by exploiting spin-orbit coupling. So here we have this ruthenium trichloride lattice, which I'll just remind you is a weakly layered structure. And in this picture, I've shown one layer. It's given by these octahedral cells, which have a ruthenium atom at its center and chlorine atoms at the external vertices. And the lattice is constructed by sharing their edges. So there's the ruthenium. Each one of those octahedra behaves effectively as one qubit or one spin degree of freedom. And then the strong spin-orbit coupling in the ruthenium atoms leads to this bond-dependent interactions, which in principle could realize this Kitaev honeycomb model, of course, with extra perturbations. Okay. And then it was recently observed by Kasara et al. That there is a half-integer thermal Hall conductance, which is consistent with this material realizing the Ising non-Abelian topological order. And so today what I'll assume is that we have a material which realizes the Ising topological order and ask, are there ways that we can probe it using electrical leads? Most of what I say, if not all, will apply more generally to any non-Abelian spin liquid which has an emergent fermion in the spectrum. In fact, it doesn't actually need to be non-Abelian, just any spin liquid that arises from bosonic degrees of freedom that has an emergent fermion in the spectrum. All right, so to do that, I would like to just review sort of the effective theories that we use for describing the Ising topological order and some related electrical systems. Okay, so the Ising topological order is shown on the right here, and then I have a closely related cousin called the P+IP superconductor on the left here. I would just like to compare and contrast these two systems as they are very similar, yet one of them has physical fermions and the other is has emergent fermions. So like I said, the Ising topological order has this emergent fermion. The counterpart in the P+IP superconductor is a physical fermion, which is just a BDG quasi-particle excitation. Both systems have non-Abelian particles. On the Ising topological order side, we have these non-Abelian Ising anyons, labeled sigma here. These are deconfined quasi-particles, and a pair of them can either appear locally like the vacuum or like the emergent fermion. On the p+IP superconductor side, we have defects, which are really vortices or defects in the spin structure. These vortices find Majorana zero modes at their core, an odd number of them. And then a pair of these vortices may appear locally like the vacuum or the physical fermion. These are not deconfined, they are really pinned to the vortices. Okay. Now their edge theories are actually identical. They're both described by a chiral Majorana fermion. However, on the p+IP superconductor side, we have to remember that these are physical fermions, whereas on the Ising topological order side, these are emergent Majorana fermions. And so we can ask a natural question. Can we gap out the interface between these two systems? And if so, what are the consequences? Okay, so here I've reproduced the two systems. This is the edge theory of the p+IP superconductor. This is the edge theory of the Ising topological order. They may have different velocities, but that's not so important. Now we can ask what kinds of interactions can we add that will gap out this interface? And so the first interaction you might think of is a simple mass term, which tunnels Majorana fermions from the p+IP superconductor to the Ising topological order. But this term turns out to be illegal. It doesn't preserve fermion parity. So recall that the left movers here carry physical fermion parity, whereas the right movers carry no fermion parity. They are non-local excitations of spins. And therefore, the product of the two carries odd fermion parity, and you cannot simply add it to the Hamiltonian. So then you can ask, what is the next most relevant interaction that we can add to the system? And that turns out to be this term. In CFT language, this is called TT bar. T is the chiral kinetic energy, T bar is the anti-chiral counterpart, and this is just the product of the two. You can think about this term as exchanging energy between these two counter-propagating Majorana modes. You can also think about it physically as taking a pair of, say, physical fermions and tunneling it into the Ising topological order, or a pair of emergent Majorana fermions, which is done, and tunneling it into the p+IP superconductor. Now we should be careful, since this term is highly irrelevant. It's got 4 Majorana operators and 2 derivatives. And so we should be careful when we say that this term gaps out the interface. Now, what one can show is at the mean field level, if lambda is large enough, that a gap will open. But I would like to give several other arguments that also convinces us that this interface can be gapped. The first set come from these microscopic models, which realize the same universal physics. So one is by O'Brien and Fenley, and the other by Ramani et al. These are translation invariant Majorana chains. The Majorana chain being translation invariant guarantees you that it's described by the same Hamiltonian as shown here, except with equal velocities in the continuum language. Namely, it's critical. And then each of them added a 4 fermion term, both of which are slightly different, but both groups show that if that 4 fermion term is cranked up strong enough, eventually it will open a gap. And one can show that if you expand that 4 fermion term in terms of low energy degrees of freedom, low energy gapless Majorana degrees of freedom, it will renormalize onto this TT bar term. The last argument, well, second to last argument I'll give is if we replace the p+IP superconductor here with the Ising topological order, then we know there ought to be an interaction which sews the two Ising topological orders together in order to create one uniform phase. It turns out the Hamiltonian which describes that interaction is exactly this term here as well. The way to see that is that the emergent Majorana fermions from one side cannot simply tunnel through the true vacuum. They need to tunnel in pairs, and this leads to the same interaction. The last argument I'll give is coming from topological quantum field theory and fermion condensation. and actually one of the inspirations for this work. So you can read more about it in this paper. And the idea is sort of gapped boundaries to topological orders are described by objects which condense such that they confine all other objects in the theory. So here I've taken the Ising system and folded it up into the P plus IP superconductor. And then I ask about, in that folded system, is there an anyon which I can condense that confines all other excitations? And the sort of particle that I want to condense here is a composite particle given by binding a physical fermion to an emergent fermion. Okay, so that composite particle is bosonic in its topological spin. It's bosonic in its statistics, but it does carry odd fermion parity. And so condensing it comes along with subtleties, which we describe in this paper. If you want a cartoon for the interface Hamiltonian, you can think about a term which binds the physical to emergent fermion, and then additional terms which fluctuate this composite particle up and down the boundary and condense it. So here's a hopping term, and then we can pair create and annihilate it as well. Okay, so now we're ready to start thinking about how we can use this P plus IP superconductor to probe this Ising topological order. So let's think about what happens when we insert an electron into the boundary of this P plus IP superconductor, as I've shown down here. It will propagate down the edge, as so, and then when it hits this interface, it has no choice but to continue propagating as a fermion. But in the Ising topological order, there are only emergent fermion degrees of freedom. And so the only way this process can conserve fermion parity is by depositing one of these composite particles into the interface, which I remind you is gapped. In order to continually do this process, we need to ground that interface so that charge doesn't build up. Okay, so we can think about this as a system that converts physical fermions into emergent fermions. All right, now we can think about
Just a moment.
Sorry,
I'm not.
Siri is yelling at me. So now we can think about some possible experiment. I will setup comes with many problems, which I'll address on the next slide. So let's think about this hypothetical experiment where we have a source on the left P plus IP superconductor and a drain on the right P plus IP superconductor. And we inject an electron into the edge of this P plus IP superconductor. Again, it will propagate down the boundary, undergo this fermion condensation process on the left-hand side, continue propagating as an emergent fermion until it hits the right-hand side, and then return as an electron in the P plus IP superconductor, doing the reverse process. Okay, this allows us to convert this electrical conductance from the P plus IP superconductors into a thermal conductance of the Ising topological order. Now note that no charge can actually pass through the Ising topological order, and so all charge is being passed through ground. Now, this would be a bad experiment because even if the Ising topological order were trivial, namely no topological phase there at all, electrons could still pass through ground from source to drain. So with that in mind, I would like to propose a slight modification where we use nu equals 1 quantum Hall phase in place of a P plus IP superconductor. In order to stabilize this fermion condensate, we need to break charge conservation. So one can do that with a superconductor, which takes this chiral electronic mode and splits it into a pair of co-propagating Majorana fermions. Then we imagine some way of adding interactions along these interfaces, maybe by pressure, maybe by sample alignment, somehow, that introduces this fermion condensate. And now we can repeat the same experiment, trying to measure a conductance between the source on the left and the drain on the right. Okay, so we insert an electron from the source. It will split into a pair of co-propagating Majorana fermions. One of them undergoes this fermion condensate process, being turned into an emergent Majorana fermion. the reverse process happens on the opposite side, and we get out an electron through the drain. So one can go through the details and work out what the conductance is. It turns out in the 0 energy and 0 temperature limit to be E squared over 2H. Now, in place of electrons going through ground, which I was using in the previous slide, the actual charge is now passing through the superconductor, but the sort of thermal current is passing through the spin liquid. All right? And now I would just like to show a control experiment where when we remove the spin liquid, this conductance goes to 0. So here's the control experiment. We tune the spin liquid to be in the trivial phase, and then ask now what is the conductance between source and drain. It turns out at 0 energy and 0 temperature, the fixed point action is described by perfect normal reflection, and therefore you end up with 0 conductance. And so I'd just like to remark that we get a difference of E squared over 2H and 0 by adding an electrically inert element, the spin liquid. All right, and in the last few minutes of my talk, I would like to describe how we can use similar circuit elements in order to probe the bulk anionic content of a non-Abelian spin liquid. So here I have a spin liquid on the right, which is the Ising topological order in this picture, the nu = 1 quantum Hall phase on the left, and then the superconductor, which is helping to mediate this fermion condensation boundary. So again, we can inject an electron from the source and measure a current through the drain, which is just coming out of the superconductor here. This electron will again split into co-propagating Majorana fermions. One of them undergoes this fermion condensation process to turn into an emergent fermion. Now, both of these physical and emergent Majorana fermions will pick up a dynamical phase as they traverse their corresponding trajectories here. The emergent Majorana fermion will also pick up a topological phase that has to do with any particles that it traverses around in the bulk spin liquid. So in the limit of 0 energy and 0 temperature, this dynamical phase drops out because it's proportional to the energy. And the only thing that we are left with is the topological part, or the topological contribution. So if the bulk has no non-trivial quasi-particle excitations, this Majorana returns with no additional phase acquired, combines with its original Majorana back into a physical electron, and one finds a conductance through the superconductor of 0. This is in contrast to the case where we have a non-Abelian Ising anyon in the bulk, which you could think about this system as coming from creating a pair of non-Abelian Ising anyons and pushing one into the boundary. In that system, the emergent Majorana fermion propagating around this edge has a non-trivial braiding statistic with that bulk Ising anyon. It will pick up a minus sign. Thus, the electron that came in returns as a whole because of this equation here. And it does so by depositing a Cooper pair into the superconductor. And so in this case, you measure conductance of 2e squared over h through the superconductor. Now, of course, this is problematic. We don't have microscopic control over these Ising anyons. So how could we possibly create a single isolated anyon in the bulk? Well, it turns out that we don't actually need a single isolated anyon. We just need an odd number of these. And so we could hope that random fluctuations in the system pair create Ising anyons, maybe by thermal fluctuations. And every time an additional Ising anyon enters that boundary, we'll see a change in the conductance from 2e squared over h to 0. And so this would result in this telegraph noise, which the quantum Hall counterparts have been described in this paper. Okay, and with that, I would just like to conclude. So I talked about how we could use a P plus IP superconductor interfaced with the Ising topological order and this fermion condensation process to convert physical fermions into emergent fermions. and then various electrical circuit elements, which allow us to give complementary experiments to this thermal Hall conductance using pure electrical conductance experiments, and also various interferometry experiments we can do in order to electrically detect non-trivial bulk anionic excitations. Okay, with that, I would like to thank you for your attention and take any questions.
Thank you very much for a very cool talk. Are there any questions? Maybe I'll just get it started. Can you go back to the proposal with the P plus IP, please?
Yep.
So
here or one over there?
Maybe a question or two here. Right. So one thing, when you have the kind of the, we want to call it a bound state, like between the real fermion and the emergent fermion on the gray patch, right? The one that trails off to the, you know, to the grounding.
Mm-hmm.
So when it's going to the grounding wire, it cannot take along the emergent fermion.
It cannot take along the emergent fermion.
So what actually, yeah, so it leaves behind, like what actually happens there, that like what is actually leaving the system and what is staying?
Yes, so there, it can only, yes, there is like a conservation of composite particles at the interface, but you could take a pair of those composite particles, annihilate the emergent fermions, and then remove the Cooper pair.
Oh, I see. I see. So it's two particles at a time that leave, or
Yep.
two bound states at a time. Okay.
Yeah, that's a good way to think about it.
I see. And so relatedly, I'm trying to understand why in this case it had to go, you know, to the grounding, but then for nu equals 1, you were able to somehow get away with that, you know, and just continue along the edge.
Yeah, so let me compare these two.
Yeah.
So the Ising topological order cannot support any charge degrees of freedom. It's purely a system of spins. So if we didn't have this, these two grounds set up, there would be no way for charge to actually go from the source to the drain. It would just be physically impossible in that universe. When we add the grounding rods, the actual charge degree of freedom, you know, we can think about this as a wire that connects these two interfaces. And so the actual physical charge can exit into the ground on this side and come out of the ground on this.
Mm-hmm. Can I just ask, so with the same reasoning that you said, you know, like you said that there's actually a pair of bound states that leave the system, right? The pair first annihilate the emergent fermions and then a fermionic pair kind of leaves. With that same reasoning, why can't, after I annihilated the emergent fermions, why can't I just send a pair continue along the P plus IP boundary, similar to what you had for the nu equals 1? Like if you just remove those groundings and, you know.
So remove the grounds, and then you want to think about actual charge traversing. I mean, there's no channel for the actual charge from the P plus IP superconductor to traverse down.
No. I'm saying the other way. Like suppose you because you want to avoid charge buildup, right? So suppose you have two bound states at the top. So where you drew the first grounding, right? Suppose you have those two pairs there, and you've annihilated the two emergent fermions. Now you're just left with two real fermions. I don't see a reason why they can't just happily carry along the P plus IP boundary.
Oh, they could. Yeah, so if you remove the grounding rod, the system would prefer perfect normal reflection.
Okay, but what's the problem with, like, then there's no buildup, right? And but there's some other.
Then there's no buildup, and there's also no conductance.
Oh, I see. There's no.
So we wanted to probe the edge states of this Ising topological order.
It's just easy to see why there's no net transfer. Like at the bottom junction, you had this emergent fermion shooting off, but there's something else canceling it. Or. Oh, it just.
Yeah. So it would, in the Ising TO, everything that's running around the edge would just continue running around the edge. It would have nowhere to go.
Yeah, right. It cannot become a real fermion. I see.
That's right.
Okay.
In the quantum Hall setup, where
I see.
you know, there's nowhere else for the charges to go.
I see.
So sort of the charge degree of freedom is forced to go through the superconductor, and if you like, the fermion parity degree of freedom through the boundary of the spin liquid.
Great, thanks. Any other questions? Yeah, I see Youngback. Please go ahead.
Hi, David. This is Youngback.
Hey, Youngback.
I have a question about this fermion condensation.
Sure.
I mean, everything just depends on this, right? In some sense.
Absolutely.
Yeah. So, so what's the precise statement? So the statement is that if you can somehow get the boundary, then fermion condensation should happen. Is that the statement, or
That's right.
Okay. So somehow so just trying to see.
So there's sort of, you know, when this fermion
the logic is just one-way flow, or actually it works both ways. So I'm just trying to figure out.
Yeah, you can turn emergent fermions into physical fermions as well. Yeah, so the logic I like to think about is you just think about injecting a fermion into the boundary of this P plus IV superconductor, and then it's a chiral boundary. This region is gapped, as long as we convince ourselves that it's gapped. That chiral fermion has to continue propagating down the edge. It has no choice. But there are only emergent fermion degrees of freedom on the right-hand side for it to propagate into. And so the only way it can do that while preserving physical fermion parity is by dropping one of these composite particles into this interface.
But you have to assume that this boundary or interface is gappable, right? Basically.
That's right. That's right.
Some
it
means.
definitely relies on it, and the interaction is strongly irrelevant. So, you know, there's many subtleties about how that could actually be realized in an experiment. But at least as a matter of principle, it seems like it is possible.
Okay, thank you.
Yeah, no problem. Thanks for the question.
Could you go back one slide?
Mm-hmm.
No, I guess it's the one where you, maybe it's ahead. It's where you show where you have the looped superconductor, the U-shaped superconductor.
U-shaped superconductor. Oh yeah, that's the good one. This one?
Yeah. So now I'm not quite sure what's happened. If I simply remove the spin, okay, you say you have no charge. You're not injecting any charge in the first. No, you are injecting charge.
If
I remove the spin liquid in the middle, why couldn't I have just conduction through the superconductor in the first place? Why do I need
the fixed point action? There's a gap to charge in the superconductor, and so the fixed point action at zero.
You're assuming that there's no Andreev.
That's right. That's right.
So it has to be weakly coupled somehow. If it's strongly coupled, you can certainly get pairs going in.
Yeah, that's right. It should be weakly coupled.
So can you be in that limit? I'm just concerned with that limit.
Yeah, in practice, I don't know.
You have a wide boundary. Why is it not possible? If the boundary is long enough, you'd think you'd get some tunneling in there. But maybe there may be an order of limits where it's okay. But
yeah, maybe in the limit of zero energy.
No, but even with zero energy, if I have tunneling purport, so if I have a weak tunneling matrix element, then to first order there's a gap, but to second order there's not a gap. I can get to second order in the tunneling matrix element, I get pairs to tunnel right simultaneously, and then there's no gap. And I'm just trying to think about whether there's any such problem in this case. If obviously if the width, I guess, of your layer which the length of the interface is long enough, I would expect that you would be able to get there would be tunneling.
Yeah, this Andreev reflection. I'd have to think about that more. So at some point I convinced myself that there wouldn't be this Andreev process.
Okay.
But maybe if it were the Andreev process, maybe we're still okay, because then you'd have a 2e squared over h conductance, which would still be distinguishable from the e squared over 2h.
Yeah, well, with two of them in series, it's 2 e squared over h,
Oh,
and two resistances in series maybe, but still you
maybe
might
squared
only
over h.
might only be e squared over h rather than e squared over 2h. That's possible. Or
Yeah.
you're saying that there would be a difference of effect. Yeah. Okay. So I don't know that I haven't thought about it at all. It's just occurred to me to worry a little bit.
No, that's a good point. Thank you.
Any other questions for Dave? If not, well, let me thank Dave again, and also Johannes, two speakers of the session, and by extension also let me thank all 8 speakers of this workshop. I definitely learned a lot these past 2 days. Let me also thank the KITP staff, both for their admin help and for IT help, in particular Claudia, Alina, Alexis, and Craig. Thank you very much. And finally, let me thank all of you for attending and making this an interactive experience. Right, and that's it. So stay safe and hopefully see some of you in the not too distant future in person. Thank you all.
Thanks, Ruben. Thank you.